Hello, class, and I want to talk about confidence intervals today. And so, when we use them, what they're good for. And so, let's start with proportions. We'll also talk about means today, and also how we can have Excel do all the calculations for us. So, if you look at the Pearson videos, there's a really good one about how to use the calculator to do the calculations for you. But I felt like the video on Excel didn't really do it justice. It talks about how you can install some extra add-ins that can do them. But we can actually create our own template that will do all the calculations for us, and that I think is actually a lot more useful for us. And there actually is already a template available in the Excel templates for the confidence intervals if you want to just download that. But we can talk about how we actually came up with all the formulas that we're using. And then if you ever need to explain how you need to do them by hand, you can see exactly how all those calculations work. So let's sort of just get at it. So say you interview 100 people and 32 of them have dogs. Well, that means that 32% of the people that you interviewed have a dog. And so if you were asked to guess, what do you think the proportion of the entire population is that has a dog? Well, your best guess would be 32%, or at least it seems reasonable that that would be the case. And so we want to see, though, there could be just some sampling error there, because it may be that something like 35% have dogs, and you just didn't happen to get as many as you expected. Or maybe it's only 30% that have dogs, and you got a few more than that. And so you don't really know how great this sample was, but you can assume that it probably is somewhere close to 32%, that it's not some sort of extreme outlier. But then the question is, well, how confident can you be about how close it is to actually 32%? And so there are sort of four things that we can see here that happened. So we have a fixed number of trials because we interviewed 100 people. And each person either had a dog or did not have a dog. The same probability was the case for each trial, assuming this was a simple random sample. Each person interviewed had the same chance of having a dog. And this one is not quite independent because every time that you interview someone, you're not going to interview the same person twice. We're sampling without replacement rather than with replacement. But the population is so much larger than the sample size that it's essentially independent. Now, there is actually a technique that you can do to adjust if you do have, like maybe this was 100 people out of 300 people at some school, and you want to make an estimate for everyone at the school. Well, then the fact that you already know a third of the people's data gives you a lot more than just what we have out of a huge population. But for our purposes, we're going to assume that it's independent because it makes things easier. And as long as the population is a lot bigger than our sample, then it doesn't really matter how much bigger. Like, it doesn't really matter if this was 1,000 people out of 50,000, or 100 people out of 50,000, or 100 people out of 50 million. We actually get just as good information either way, because in either case, the sample is so much smaller than the population that it's really just the sample size that matters. And so if you looked at these four characteristics and immediately thought, oh, that's a binomial distribution, you are absolutely correct. The number of people who you interview who have a dog will follow a binomial distribution. And so we can look at some statistics of the binomial distribution. If you remember from chapter 5, the mean of the binomial distribution is just the proportion of success times the number. That seems fairly straightforward. just by the definition of what probability is. On average, you just take your proportion and multiply it by the population size or sample size, and that gives you the number who have whatever characteristic it is. The standard deviation was not quite as intuitive, but we had a formula for it, which is the square root of n times p times 1 minus p, or your book likes to say times q. Now, if we want to convert these to proportions, remember the proportion is you just take the number of success divided by the sample size, and you say, okay, well, if that's the number of success is n times p, then the mean proportion is just going to be p itself. And this should be very intuitive as well. On average, your sample proportion will match the true proportion. Seems pretty straightforward. And then the sample proportion standard deviation, though, is we just take this and we divide by n. And you can think, well, square root of n divided by n. The square root cancels, and then you get a square root n in the denominator. And so it ends up just being the square root of p times 1 minus p divided by n. And so we often call this the standard error. If you remember chapter 6.4, when we talked about the central limit theorem, we also had the standard error, because it is the error from the sample versus the true proportion. Remember, a standard deviation is the standard amount that you deviate from the mean, and so this is the standard amount that you deviate from the true proportion, since the mean sample proportion is the true proportion. And we can also use a normal distribution to approximate a binomial, with the caveat that you want at least 5 success and at least 5 failures in your sample. Otherwise, if you have a very extreme, an event that basically never happens or basically always happens, it's difficult to find the sort of more precision in there. And so that's why we want at least 5 successes and at least 5 failures. All right. And so now if we sort of think about this, okay, so let's say that we want to find an interval of values. So we know in this case it should be around 32%, plus or minus some margin of error. And we want to say, okay, so how far from 32% might we typically be? And so for this, we're going to want to establish something called a confidence level. And so the confidence level is how often you want your interval to contain the true parameter. All right. So it's however often you want to contain the true parameter. Now you're never going to contain the true parameter 100% of the time unless you say something like somewhere between 0 and 100% of people own dogs. Well, okay, yeah, but that's completely useless information. Of course that's true. But we can say up to some smaller level of confidence, like 95% confidence, what is the true proportion who own a dog. And so the way that we can do that is we can look at a normal distribution and we say, okay, so if we want 95% to be in the middle, then that means that we need to find, well, what is the z-score associated with the smallest? Well, there's 5% that's not in the middle, and 5% divided by 2 is equal to 0.025. And so if you think about it, each of the tail on the left and the tail on the right would both be 0.025. And so that's why we call this critical value. The critical value is the part that separates the middle from the end area, is called z alpha over 2, because alpha which is 1 minus the confidence level. So alpha is how often you're willing to be wrong. And the tail is half of alpha. So each tail is half of alpha, since there are 2 of them. And so to find the critical value, so find the z-score associated with alpha over 2 in the tail. All right. And so that's what we're going to want to do here, is to basically find this z-score associated with it. So let's actually set up doing some of these calculations here. So let's actually put in what we know. We know the number of success. All right. Whoa, that was a bit big. We know our sample size. All right. And we know our confidence level. All right, so those are the sort of the 3 big ones. And if you're putting it in a TI calculator, these are the only 3 inputs that you need. And so one thing that we want to find, as we said, is we have our standard error. That's going to be important to us. So we have a standard error. We also talked about a critical value. All right, so we'll talk about how to get that. And then together we can get the margin of error. And once we have the margin of error, we can find our confidence interval min and our confidence interval max. All right. And so let's actually put in the data that we have. So let's see, we have 32 people who have dogs and a sample size of 100. And let's say we want to find a 95% confidence interval. All right. And so to get our standard error, well, let's just look at it. The standard error. Oh, so one thing that we'll actually want is a sample proportion. I'm actually going to add that here, or insert. There we go, insert sample proportion. Because sometimes you're actually given the sample proportion directly. So our sample proportion is just the number of success divided by our sample size. So we can just put that in as a formula, and we're good. And so now we have our standard error. And so in this case, we can say, well, our standard error is equal to the square root of, well, we don't know what p is. That's what we're trying to figure out. But our best estimate is the sample proportion. So we're just going to use that. And then we're going to multiply by 1 minus it. Whoopsie. 1 minus it. And then divide by the sample size as so. And we hit enter, and there is our standard error. So we would typically expect that our poll would actually have an error of almost 5 percentage points. All right, so really, it wouldn't be too unreasonable to think that maybe it's actually 37% or 25 or 27%. But it's even more than that, because if we want 95% confidence, that's not just one standard deviation from the mean. And so the way that we get the critical value then, so let's look at the critical value. Well, we would want it to be the tail of half of the alpha. All right. So if you think about this, alpha was 0.05. All right. So we would really want 1 minus the confidence level over 2. And we really need the normal inverse, because the inverse normal will give us the size of that, will give us the z-score associated with that tail. So it's norm.inv of that. And we can actually even say norm.s.inv because we want it to be a standard normal. And so this could be the input that we use. So we'll do equals norm dot s dot inv, and we'll just do 1 minus the confidence level divided by 2. All right. And now that's actually negative, because if you think about it, if we look at this table here, we found the left tail, which would be with a negative critical value. So if we want the positive critical value, we can just put a minus sign in front of this formula and hit enter. All right, so we would actually want it to be with a minus sign in front. All right, and then if we think about the margin of error, well, that's one standard deviation of error. This is the number of standard deviations of error that you want to include. And so the margin of error is just the standard error multiplied by the critical value. And that's the formula that you see in the textbook. And then you say, okay, well, that's our margin of error. And so you say, well, what is the actual confidence interval itself? Well, we know our sample proportion is 0.32. And so 0.32 is the best guess. But the error could be up to, we'll just say 0.09. So we take 0.32 minus 0.09 and 0.32 plus 0.09, because we want to do plus or minus the margin of error, and that would give you the value. So we just do equals sample proportion plus margin of error, enter, and then equals, and then we do the sample proportion minus the margin of error, and we hit enter. And whoopsie, I got this reversed. It should be minus and plus. There we go. So the minus is the minimum and plus to get the maximum. And so we can say that we are 95% confident that the true proportion is between, we'll just say 23% and 41%. All right. So, and remember, this is the true proportion of people who own dogs based on this survey. So 32% is our best guess, but anywhere from 23 to 41% would be reasonable. And there is a 5% chance whenever we go through collecting data and making the confidence interval that we end up just getting an outlier value. So we can actually copy and paste all of these formulas down. And one of the great things about Excel is that once you have these sort of templates, you can compare things. All right. So I'm going to get rid of this from the screen right now. If you want to look at that formula again, just back up the video, and we're going to make some more space. And so let's say we wanted, instead of 95% confidence, to have 99% confidence. Notice we get a larger critical value and a larger margin of error, and thus a wider confidence interval. The reason why is because if we want to capture the true proportion 99% of the time, we're going to need a larger window than we would just to capture it 95% of the time. Another cool thing we can see is, well, what if we interviewed more people? And let's say the number, it was 64 out of 200. All right, and then we will simply bring down our formulas some more. I think we can actually highlight these and bring them all down at once. Oh, no, I guess not. Oh yeah, so I need a confidence level. Let's put back at 95%. So notice when we increase our sample size, we decrease the standard error, and thus we decrease our margin of error. And so the larger our sample size is, the smaller our margin of error is. And that's because of the general principle we get through the central limit theorem, that the larger our sample size is, the more likely it is that our sample proportion, or sample mean, is close to the true parameter, in this case, the true proportion. And so we can see by just having all the same stuff copied over, except that we increase our sample size. So instead of 64 out of 200, maybe it's 128 out of 400. And now we have an even smaller standard error still. Notice we actually have exactly half the standard error, because the square root of 4 versus 400 is exactly twice the square root of 100, 10 versus 20. And so the standard error is exactly half as much. And so that is a great way to figure out the true, basically where we would expect the true proportion to be. And we can, of course, then once we have this template, if we want to change anything, like decrease the confidence level, we don't need to be 95% confident. Maybe messing it up 10% of the time is okay. We get a smaller margin of error, and we can say that's where the true proportion is likely to be. So I'll have another follow-up with means very soon. So thank you for watching.